A black hole can stretch you like spaghetti, and scientists actually call this spaghettification, which sounds funny, until you realize it means your body would be pulled apart, atom by atom, starting with your feet, if you fell in feet first, because gravity gets stronger, the closer you get to the center, and the difference between the pull on your feet and the pull on your head would rip you into a long, thin string of atoms. Black holes are not actually holes at all, but instead they are objects in space that have so much stuff packed into such a tiny space that their gravity becomes incredibly strong, stronger than anything else we know of in the entire universe. The smallest black holes we know about are about 3 times heavier than our sun, but squeezed down to a size smaller than a city, while the biggest black holes are billions of times heavier than the sun and could swallow our entire solar system. Nothing can escape from a black hole once it crosses a point called the event horizon, which is like an invisible boundary around the black hole. And once you cross it, you can never come back, no matter what you do. Even light cannot escape from a black hole. And since light is the fastest thing in the universe, this tells us just how powerful these objects really are. Because light cannot escape, we cannot actually see a black hole directly, which makes them invisible. But we can see them by watching how they affect things around them, like stars and gas clouds. When stuff falls into a black hole, it often forms a spinning disk called an accretion disk that gets so hot it glows brighter than billions of stars. And this is one way scientists find black holes. The center of a black hole is called a singularity, and this is where all the mass gets crushed into a point that might be infinitely small. Though scientists are not completely sure what happens there because our math breaks down. But here is where things get really weird, and you will not believe what happens to time near a black hole. Because if you watched your friend fall into one from a safe distance, you would see them slow down until they seemed to freeze right at the edge, never actually crossing the event horizon, even though, from your friend's point of view, they would fall right through without noticing anything special at that moment. Time itself moves slower near a black hole, and the closer you get, the slower time moves compared to someone far away. So if you could somehow orbit close to a black hole for a few hours and then come back, everyone you knew on Earth might have aged decades or even centuries. Albert Einstein predicted black holes with his theory of general relativity back in 1915, but he did not think they could actually exist in real life, and it took other scientists many years to convince the world that these objects were real. The first person to really understand what Einstein's equations meant for black holes was Karl Schwarzschild, who was a German scientist serving as a soldier in World War I, and he figured out the math while he was in the trenches fighting, which is amazing when you think about it. For a long time, scientists called these objects frozen stars or dark stars because they did not like the term black hole, which was not used until 1967 when a scientist named John Wheeler started using it, and the name stuck. The nearest black hole to Earth that we know about is probably around 1,000 light-years away, which sounds far, but in space terms, that is actually pretty close, like being neighbors in the cosmic sense. What would really blow your mind is learning that there is a supermassive black hole right at the center of our own Milky Way galaxy, and it weighs about 4 million times as much as our Sun, and scientists call it Sagittarius A star. And it is sitting there right now about 26,000 light-years from Earth. Almost every large galaxy has a supermassive black hole at its center, and these monsters help shape how galaxies form and evolve over billions of years. Black holes were probably formed in different ways depending on their size, where stellar black holes form when giant stars run out of fuel and collapse in massive explosions called supernovas, while supermassive black holes might have formed from huge clouds of gas in the early universe, or from many smaller black holes merging together. When a star is massive enough, at least 8 to 10 times the mass of our sun, it can eventually become a black hole. But most stars, including our own sun, are not heavy enough and will end their lives in different, less dramatic ways. Our sun will never become a black hole because it does not have enough mass, and instead it will eventually become a white dwarf, which is a hot, dense object about the size of Earth. If you could replace the sun with a black hole of the same mass right now, Earth would not get sucked in because gravity at our distance would stay the same, though we would freeze to death without the sun's light and heat. Black holes do not actually suck things in like a vacuum cleaner as many people think, but instead objects have to get pretty close before the gravity becomes strong enough to pull them past the point of no return. Scientists detected gravitational waves for the first time in 2015, and these waves were created by two black holes that crashed into each other and merged about 1.3 billion years ago, and the waves traveled through space all that time before reaching Earth. Gravitational waves are ripples in space and time itself, and they happen when massive objects like black holes accelerate or collide, and Einstein predicted these too, though they were only confirmed 100 years later. When black holes merge, they create a new, bigger black hole and release enormous amounts of energy as gravitational waves. And some of these collisions release more energy in a fraction of a second than all the stars in the universe combined. In 2019, scientists showed the world the first ever image of a black hole, and it showed the shadow of the supermassive black hole at the center of a galaxy called M87, which is 55 million light-years away. The image showed a dark circle surrounded by a bright orange ring of hot, glowing gas. And to take this picture, scientists had to connect radio telescopes from all around the world to create one Earth-sized telescope. The black hole in M87 is truly enormous, with a mass of about 6.5 billion suns, and the event horizon is about 2.5 times smaller than the orbit of Neptune. In 2022, scientists released another image showing Sagittarius, a star, the black hole, at the center of our own galaxy. And even though it is much closer to us, it was actually harder to photograph because the gas around it moves and changes very quickly. You might wonder what it would actually feel like to fall into a black hole. And the answer depends on the size. Because with a small black hole, you would be torn apart by tidal forces long before reaching the event horizon, but with a supermassive black hole, you might not feel anything strange at all as you crossed the event horizon, though you would still be doomed. The gravity difference between your head and feet is what causes spaghettification, and this effect is much stronger near small black holes than near supermassive ones, because the event horizon of a supermassive black hole can be millions of miles from the singularity. Once inside the event horizon, you would be pulled toward the singularity, and there would be no way to escape. And no one knows exactly what would happen when you reach the singularity, because the laws of physics, as we understand them, break down completely. Some scientists think there might be something called a firewall right at the event horizon of a black hole that would burn anything crossing it instantly into radiation. But other scientists disagree, and this debate is still going on. Stephen Hawking, who was one of the most famous scientists who studied black holes, discovered that black holes are not completely black because they actually give off a tiny bit of radiation now called Hawking radiation. Hawking radiation happens because of weird quantum effects right at the event horizon, where pairs of particles pop into existence and one falls into the black hole while the other escapes. And this means black holes very slowly lose mass over time. If you waited long enough, trillions and trillions and trillions of years, a black hole would eventually evaporate completely from Hawking radiation and disappear. But for black holes the size of stars, this would take much, much longer than the current age of the universe. Smaller black holes evaporate faster than larger ones, so a tiny black hole, the mass of a mountain, would evaporate in a fraction of a second, releasing an enormous explosion of energy. The gravity near a black hole is so strong it actually bends light, and this creates an effect called gravitational lensing, where light from stars or galaxies behind the black hole gets bent around it, making it possible to see multiple images of the same object, or creating rings of light. If you were orbiting close to a black hole, you could theoretically see the back of your own head, because light from behind you would curve around the black hole and come back to your eyes, though you would have bigger problems to worry about. Inside a black hole, space and time switch roles in a way that is very hard to understand, and what this means is that once you cross the event horizon, moving toward the singularity becomes as unavoidable as moving forward in time is in normal space. Some scientists have wondered if black holes could be connected to white holes, which would be the opposite of black holes, where instead of nothing being able to get in, nothing could stay in, and everything would be pushed out, but we have never found any evidence that white holes actually exist. There is also a theory that black holes might be connected to other parts of the universe, or even other universes, through tunnels called wormholes. But if these exist, they would probably be incredibly unstable and collapse immediately if you tried to go through one. Could you use a black hole as a time machine? And technically, yes, if you orbited close to one, you would travel into the future compared to people far away. But you could never travel backward in time, and you would have the problem of surviving near the black hole and getting away from it afterward. If Earth somehow fell into a black hole, we would be ripped apart long before reaching the event horizon, because the tidal forces would tear our planet into smaller and smaller pieces and eventually into individual atoms, and there would be nothing anyone could do to stop it. The good news is that there are no black holes close enough to Earth to pose any danger, and none on a collision course with our solar system, so we can sleep safely at night without worrying about being sucked into one. Black holes grow by eating matter that gets too close, including gas dust stars, and even other black holes, and the more they eat, the bigger they get, and the stronger their gravity becomes. When black holes feed on gas and stars around them, they can produce jets of material and energy that shoot out from near the event horizon at speeds close to the speed of light, and these jets can be millions of light years long. These jets are created by the powerful magnetic fields and incredible heat near the black hole, and they are so energetic they can affect entire galaxies and even prevent new stars from forming in some regions. Quasars are extremely bright objects in the distant universe, and they are actually supermassive black holes at the centers of young galaxies that are feeding very actively, and they can outshine all the stars in their galaxy combined. We see quasars as they were billions of years ago because their light has taken that long to reach us, and they were much more common in the early universe when galaxies were forming and black holes had more food to eat. Some black holes spin extremely fast, and the fastest spinning ones rotate hundreds of times per second, which is hard to imagine for something that massive. And this spin affects the space around them, dragging it along in a process called frame dragging. If a black hole is spinning and you were orbiting around it, you would be dragged along in the direction of the spin whether you wanted to or not, because the black hole literally drags space and time with it as it rotates. There is a region around a spinning black hole called the ergosphere, where space itself is being dragged around so fast that nothing can stay still relative to the outside universe, and in theory, you could extract energy from this region using a process called the Penrose process. Scientists believe intermediate mass black holes exist between stellar mass and supermassive black holes, weighing hundreds to thousands of times the mass of the Sun. But these are harder to find, and we have only a few candidates that might be this type. Some scientists think primordial black holes might have formed in the very early universe just after the Big Bang from areas where matter was squeezed together more densely than surrounding areas. Though we have not confirmed these exist yet. If primordial black holes are real, and some are tiny. They could be all around us, passing through Earth all the time, but they would be so small and would pass through so quickly, we would never notice. There is a famous thought experiment called the black hole information paradox, which asks what happens to information about the stuff that falls into a black hole, because quantum mechanics says information cannot be destroyed, but it seems to disappear in a black hole. Stephen Hawking spent decades working on this problem and eventually came to believe that information is not lost, but instead gets scrambled and eventually comes back out in the Hawking radiation, though in a form that is impossible to read. A stellar black hole passing through a cloud of gas or dust might not give off much light or radiation if it is not actively feeding, making it very hard to detect unless it happens to pass in front of a star and we notice the star's light being bent or dimmed. Binary systems, where a black hole orbits a normal star, are excellent places for scientists to study black holes because gas from the star gets pulled toward the black hole, forming an accretion disk that heats up and gives off X-rays we can detect with special telescopes. Cygnus X1 was one of the first black holes ever identified in 1971, and it is part of a binary system about 6,000 light-years away, where a black hole is pulling gas from a blue supergiant star. Stephen Hawking famously made a bet that Cygnus X1 was not actually a black hole, and he lost that bet in 1990 and had to buy a subscription to a magazine as the penalty, which he did gracefully. If two galaxies collide, which happens sometimes over millions of years, the supermassive black holes at their centers will eventually spiral toward each other and merge, creating an even more massive black hole and sending out gravitational waves. Our Milky Way galaxy is actually on a collision course with the nearby Andromeda galaxy, and in about 4 billion years, they will crash together, and eventually their central black holes will merge. But Earth will probably be fine, though the night sky will look very different. The final stages of a black hole merger happen incredibly fast, with the two black holes circling each other faster and faster until they collide and become one in a fraction of a second, releasing a huge burst of gravitational wave energy. Some scientists have proposed that our entire universe might be inside a black hole, and that every black hole might contain a universe inside it, which is a mind-bending idea, though there is no way to test this, and most scientists do not think it is likely. If you could hover just outside the event horizon of a black hole using a rocket to fight the gravity, you would need an incredible amount of fuel because the gravity is so strong, and from your perspective, time would be passing much faster in the rest of the universe. Black holes come in different types based on their properties, where the simplest is a Schwarzschild black hole, which does not spin and has no electric charge, while the most complicated is a Kerr-Newman black hole, which spins and has charge. Most real black holes are probably Kerr black holes, which are described by only two numbers, their mass and their spin, showing that despite forming from complicated stars, they end up remarkably simple. This simplicity is summed up in a phrase scientists use, that black holes have no hair, which means they do not have complicated features on their surface, and two black holes with the same mass and spin are identical, no matter what fell in to make them. The event horizon of a black hole is not a physical surface you could touch, and if you fell through it, you would not feel anything special at that moment, because it is just an invisible boundary in space, but it represents the point of no return. Outside the event horizon, there is another boundary for spinning black holes called the static limit, where the dragging of space becomes so strong you cannot remain stationary, no matter how hard you try, and you are forced to move in the direction the black hole is spinning. Between the static limit and the event horizon is the ergosphere, where the weird physics of frame dragging is strongest, and where in principle, energy could be extracted from the black hole's rotation. If you somehow manage to survive inside a black hole, which is impossible because you would be destroyed, you would see very strange things like the entire outside universe appearing to speed up and age before your eyes because of time dilation effects. The mathematics describing black holes involves Einstein's field equations from general relativity, which are incredibly complicated, and there are only a few exact solutions that describe black holes, and scientists are still discovering new things about them today. Black holes play a crucial role in the universe by helping recycle matter, concentrating energy, and possibly helping seed the formation of galaxies and large-scale structures. Though scientists are still figuring out all the details, some dying stars create neutron stars instead of black holes, and these are incredibly dense objects where a teaspoon of material would weigh billions of tons, but they are not quite dense enough to become black holes. And that is the difference between being massive enough to collapse completely or not. The boundary between whether a dying star becomes a neutron star or a black hole depends on its mass, with the dividing line being around 2 to 3 times the mass of the Sun compressed into a small space, and anything heavier will collapse into a black hole. When scientists talk about the size of a black hole, they usually mean the diameter of the event horizon called the Schwarzschild radius, which for a black hole with the mass of the Sun would only be about 3 kilometers across. For the supermassive black hole at the center of our galaxy, the event horizon is about the size of the orbit of Mercury around the Sun, showing that more massive black holes have proportionally larger event horizons. The density of a black hole, calculated by dividing its mass by the volume inside the event horizon, actually goes down as the black hole gets more massive, which seems strange, but it is because the volume increases faster than the mass as black holes grow. This means a supermassive black hole could have an average density less than water if you calculate it this way, though this is a bit misleading because all the mass is at the singularity, and the space inside the event horizon is mostly empty. Black holes affect the orbits of stars around them, and by watching stars orbit around the invisible centers of galaxies, scientists can calculate the mass of the supermassive black holes there. And this is how we know Sagittarius A star weighs 4 million suns. Some stars orbit so close to Sagittarius A star that they complete an orbit in just a few years, even though they are moving at a few percent of the speed of light, and these orbits proved that there really is a massive compact object there. One star called S2 has been tracked orbiting Sagittarius A star since 1995, and its closest approach brings it within about 1 light day of the black hole, and watching it has let scientists test Einstein's theory of general relativity in the strong gravity environment near a black hole. When scientists imaged the black hole in M87, they noticed the bright ring was brighter on one side than the other. And this is because the gas on one side is moving toward us, boosted by the rotation of the black hole, while the other side is moving away, appearing dimmer. The jet coming from M87's black hole extends for about 5,000 light years, and particles in the jet are moving at 99% the speed of light, showing the incredible energies involved. Not all black holes have jets, and scientists think jets form only when black holes are spinning fast and feeding actively with the right conditions in the magnetic fields and accretion disk around them. If you fell into a spinning black hole instead of a non-spinning one, the experience would be even weirder, because there would be regions where you could theoretically orbit in strange ways, though you would still ultimately be pulled to the singularity. Some theoretical physicists have studied what would happen inside a rotating black hole, and the math suggests you might encounter a ring-shaped singularity instead of a point. And there might even be regions where the structure of space and time becomes completely different from anything we know, though this is all theoretical. There is an idea that if you fell into certain types of rotating black holes, you might not hit a singularity at all, but instead pass through to another region of space or even another universe. But this is purely theoretical, and most scientists think real black holes would not work this way. The The concept of a naked singularity is a singularity without an event horizon, which would let us see the strange physics at the singularity directly. But most physicists believe the cosmic censorship hypothesis, which says nature prevents naked singularities from forming, and every singularity is hidden behind an event horizon. If naked singularities did exist, they would break many of our ideas about physics and causality, and could lead to strange effects, like time loops. But there is no evidence they exist, and the cosmic censorship hypothesis seems to hold in all cases we have studied. Black holes have been featured in many science fiction movies and stories, though most of them get the science wrong in various ways, like showing people surviving way too close to black holes, or showing black holes as swirling drains in space. The movie Interstellar from 2014 actually had scientists working as consultants to make the black hole scenes as accurate as possible, and the visual effects were based on real calculations using Einstein's equations, though they still took some creative liberties. The black hole in Interstellar, called Gargantua, was portrayed as a fast-spinning, supermassive black hole with a beautiful accretion disk that appears to wrap above and below the black hole because of gravitational lensing. And this was one of the most scientifically accurate depictions in any movie. Some people worry about scientists creating tiny black holes in particle accelerators like the Large Hadron Collider. But this is not possible with current technology, and even if it were possible, the black holes would be so small they would evaporate instantly from Hawking radiation before doing any damage. Even if a tiny black hole did not evaporate instantly, it would be so small that it would pass right through normal matter most of the time, without interacting, because atoms are mostly empty space, and the black hole would be smaller than an atom. The amount of energy needed to create a black hole in a particle accelerator is far beyond what we can produce, and would require smashing particles together at energies trillions of times higher than what the Large Hadron Collider can achieve. Dark matter is different from black holes, even though both are dark and involve gravity, because dark matter is probably some kind of unknown particle spread throughout the universe, while black holes are concentrated objects, and we can detect black holes by their effects on visible matter, while dark matter is more subtle. Some scientists once thought dark matter might be made of many small black holes called MACOs, which stands for massive compact halo objects. But observations have ruled out this idea, and most scientists now think dark matter is some kind of exotic particle we have not discovered yet. When gas falls into a black hole and gets very hot in the accretion disk, it gives off radiation across the spectrum from radio waves to X-rays and gamma rays, and by studying this radiation, scientists can learn about the black hole's mass spin and what it is eating. The temperature of the accretion disk around a black hole can reach millions or even billions of degrees, making it one of the hottest places in the universe. And this heat comes from friction as gas spirals inward, and from the gravitational potential energy being converted to heat. Because black holes are so extreme, they provide natural laboratories for testing the limits of physics, including general relativity, quantum mechanics, and thermodynamics in ways that would be impossible to recreate on Earth. Stephen Hawking showed that black holes have a temperature and entropy, which are properties we usually associate with thermodynamics and everyday objects like gases, and this connected black holes to one of the fundamental laws of physics, the second law of thermodynamics, which says entropy always increases. The entropy of a black hole is proportional to the area of its event horizon, rather than its volume, which is strange and suggests that all the information about what fell into the black hole might somehow be encoded on its surface in a holographic way. This idea has led to something called the holographic principle, which suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary, which is a profound idea that is still being explored in theoretical physics. Gravitational waves from merging black holes have opened a completely new way of observing the universe called gravitational wave astronomy, which lets us detect events we could never see with light because some events do not produce any light at all. Since the first detection in 2015, scientists have found dozens of black hole mergers using gravitational wave detectors like LIGO and Virgo. And each detection teaches us more about how black holes form, merge, and behave. One surprising discovery from gravitational waves is that there seem to be more mid-sized black holes than scientists expected, with some mergers producing black holes in a range that was thought to be rare, based on theories of how stars die. Scientists have also detected what appear to be mergers between black holes and neutron stars, which are exciting because they can produce both gravitational waves and light from the material torn off the neutron star, giving us multiple ways to study the event. The future of black hole research is bright, with better gravitational wave detectors being built, better telescopes to image black holes, and new theoretical work to understand the quantum nature of black holes and what really happens at singularities. Some scientists hope that studying black holes will eventually lead to a theory of quantum gravity, which would unite Einstein's general relativity with quantum mechanics, and could explain what happens at the singularity and resolve paradoxes like the information paradox. There are ideas that space and time themselves might emerge from something more fundamental, and that singularities might not be real, but instead represent places where our current theories break down and need to be replaced with something deeper. Black holes remind us how much we still do not know about the universe, and how the most extreme objects can teach us about the fundamental laws of nature and push our understanding to its limits. Even after decades of study, black holes continue to surprise scientists with new discoveries, and there is surely much more to learn about these fascinating objects that represent some of the strangest predictions of Einstein's revolutionary theory of gravity. And these objects that once seemed impossible are now known to be common throughout the universe, playing crucial roles in shaping galaxy stars and the cosmos itself, making them not just curiosities, but essential parts of the story of how our universe works and evolves over billions of years.